So today we want to extend our discussion of gases and the gas laws and show a couple of applications for how we can use these gas laws in other types of problems. For instance, how could this play out if we were dealing with the gas laws in stoichiometry? Look at this first equation or first example. We've got a chemical reaction that takes place in an airbag and it occurs when severe deceleration, slamming into something, causes a steel ball to compress, and it ignites a detonator cap, and it causes the sodium azide to decompose explosively. Now it produces nitrogen gas. The nitrogen gas is pretty unreactive, so it's a good thing to produce. You wouldn't want to produce oxygen gas or hydrogen gas in a car wreck because that would go on and react explosively, perhaps when it was subjected to sparks or heat from a fire or something. So this is the reaction we're dealing with, and it's asking us to find how many liters of nitrogen gas under these conditions of temperature and pressure can be produced from the decomposition of 75 grams of sodium azide. So the first thing that I would do if I were attacking this problem would be to look at my liters of nitrogen. I'm trying to find liters of nitrogen. It gives me a pressure and a temperature. So I can just assume that I'm going to be using the Pervert equation to find this, since we're dealing with a gas that is not at STP. It's not at 760 millimeters of mercury and 0 degrees Celsius. So we're going to need the Pervert equation to solve this. So we start that out. We know that PV equals nRT. And we're solving for volume, so that becomes nRT over P. And I start trying to plug in values for that. The volume is equal to, and I look for a number of moles. Now I'm dealing with nitrogen gas, and I look for numbers of moles of nitrogen gas, and I don't see anything. And that creates a big problem because without a number of moles for that equation, I end up with two variables in that equation, two unknown variables that I can't possibly solve the equation with that. So since I can't get the moles of nitrogen gas, there must be other information that would help me do that. I need moles of nitrogen gas in order to solve my Pervert equation. Does it give me other information? Well, it doesn't give me anything about nitrogen, but it sure gives me something about the sodium azide. It tells us that we have 75.0 grams of sodium azide. With a balanced chemical equation, this gives me all the information I need in order to solve a stoichiometry problem to get moles of nitrogen from my 75 grams of sodium azide. So let's do that real quick. We've got 75 grams of our sodium azide straight to a molar mass. The molar mass of sodium azide is 65.02 grams per mole. And the fact that there are 3 moles of nitrogen for every 2 moles of sodium azide gives me a value of 1.73 moles of nitrogen gas. So that gives me the value I need to substitute in for moles over here in my equation. So let's plug that value into our equation. We now see that we have 1.73 moles of our nitrogen gas times 0.0821 liter atmospheres per mole Kelvin, lattimolts. And we have a temperature value then, 20 degrees Celsius, 293 kelvins. Don't forget to add that 273. Now on bottom we need a pressure. Now this is an R-driven equation, remember, and it gives us a pressure of 750 millimeters of mercury. So the first thing we're going to need to do real quick is to do a side calculation. 750 millimeters of mercury, and we know that for every atmosphere there are 760 millimeters of mercury. That gives us a value of 0.9868 atmospheres, and that's what's going to go in for our pressure value in our equation down here. So 0.9868 atmospheres. Notice what that's going to do. That's going to cancel moles, cancel atmospheres, cancel kelvins, and we're left with liters, which is exactly what we want for our answer. That gives us to 2 sig figs, 42 liters of our nitrogen gas for our answer. So that's one way you could use this kind of equation in your use this Pervert equation in a stoichiometry problem. So let's go on with this next problem then and see how this one plays out. It says we have gaseous oxygen reacting with aqueous hydrazine, which is a rocket fuel, to produce water and gaseous nitrogen according to this balanced equation. So we're going to start with a solution that is 180 grams of hydrazine, and we're going to react that with 15 liters of oxygen. And the conditions are 1200 millimeters of mercury and 20 degrees Celsius for the oxygen. And it's asking us to find how many grams of water as a byproduct. Now, at first glance, you might not recognize what type of problem this is, but we've just been given a question where we're trying to find how much of a product is being produced, and we're given information about both of the reactants. Yeah, we're dealing with something more complicated than our Chem 1 problems, but this is a limiting reagent problem. A limiting reagent problem. Again, it follows the pattern of information about the reactants, 2 of the reactants, and then trying to find the product. Now, if you remember, when we're dealing with limiting reagents, our first goal is to find the number of moles of each of the reactants present, and then divide by the coefficient, which really isn't going to be an issue in this particular problem since it's a 1-to-1 reaction. But divide by the coefficient and come up with that relationship, that mole relationship, choose the smallest number, and that's our limiting reagent. So let's get done with that part first, with the limiting reagent part. For the N2H4, for our hydrazine, we've simply got a molar mass problem. Just converting using molar mass. And the molar mass of hydrazine is 32.06 grams per mole. And we end up with 5.61 moles of our hydrazine. And that's just like we did in Chem 1. Now, the problem here, though, is that we're not given that kind of information about oxygen. We're given a volume, we're given a temperature, we're given a pressure. And that's just classic information for using the Pervert equation. So that's what we're going to do. PV equals nRT. We're solving for N. We want to find moles, and the number of moles is going to be equal to PV over RT. The pressure, once again, we're going to need a side calculation on the pressure because it gives us 1200 millimeters of mercury. We know that there's 1 atmosphere for every 760 millimeters of mercury. When we divide that out, we end up with 1.579 atmospheres. So that's the value that's going to go in for our pressure down here in our Pervert equation. So I'll do it in the same color so I don't start getting things a little confusing. 1.579 atmospheres times the pressure, times the volume, which it already gave us in liters, so that's nice. We're going to divide that by R, 0.821 lattimolts, liter atmospheres per mole Kelvin, and our temperature of 20 degrees, which is going to be 293 kelvins. So let's look at our units and make sure that we're getting those to cancel right. Atmospheres are canceling, kelvins canceling. We're having our liters cancel. We're ending up with moles on the bottom of a bottom term. Remember that we end up divided 1 divided by 1 over moles tells us that our units are going to be moles. So N in this case ends up being 0.9846 moles of our oxygen gas. So now that we know moles of both of these, we are going to choose the smallest number value. Neither one of them had to be divided by coefficients since they both had coefficients of 1 in the balanced equation. So it ends up with oxygen as the limiting reagent. So keep in mind that now that we know that oxygen is a limiting reagent, the rest of our problem must start with that. And all we're doing now is taking our moles of oxygen and determining how many grams of water that will be. Just another, I'm going to give myself a little more room, just another stoichiometry problem. So starting with that value of 0.9846 moles of oxygen, we can go straight to our mole ratio, which is 2 moles of water, 2 moles of water for every 1 mole of oxygen. And the fact that there's 18.02 grams of water per mole of water gives us a value to 2 sig figs of 35 grams of water. So there's our second stoichiometry and gas law mixed problem. So it's just another way to use that information. We can also take something we learned about earlier in the year, mole fraction, and we can, if we know the mole fraction of the gases in a container, we can determine the partial pressure of each one of those. Because remember, if you've got gases in a container, they're all going to be at the same temperature, same pressure, same volume, so we can relate the number of moles to each other because of Avogadro's law. So mole fraction, remember, is the moles of a substance divided by moles total. It's just like percent. The only difference is we're not going to mess with the times 100 divided by 100. We're not going to mess with having to change the decimal, move the decimal place. So the first thing it asks is that to take that sample of hydrogen and oxygen that has 5.1 moles of hydrogen and 2.4 moles of oxygen and find the mole fraction of each of the gases. So remember, the mole fraction of hydrogen is going to be the 5.1 moles of hydrogen divided by the total 5.1 plus the 2.4 moles of our oxygen, or 7.5, and when we divide that, we end up with 0.68 for a mole fraction for our hydrogen. The mole fraction of oxygen then is going to be 2.4 over that 7.5, the total, 5.1 plus 2.4, partial over total, just not the times 100, and we end up with 0.32 for the mole fraction. Remember, quick double check, all of your mole fractions should add up to 1.0, right, or to 1. Just like percentages have to add up to 100. So we could say, if we were dealing with percentages, we could say that 68% of this container, 68% of the particles of this container were hydrogen, 32% is oxygen. We're just not going to mess with that times 100. Because when we get down to this next equation, we can see that we can find the partial pressure based on those mole fractions. We're going to take the total pressure and multiply it by the mole fraction. It's just like a percent problem. We're just not going to deal with the moving the decimal place. So the partial pressure of the gas is equal to the mole fraction of that gas times the total pressure. So look at the example problem. What would be the partial pressures of each of the gases in the above example if the total pressure is 824 millimeters of mercury? Well, look at the partial pressure of hydrogen is going to be its mole fraction, which was 0.68, times the 824. I'll go ahead and put in the units. Just like a percent problem. If this were 68% of that pressure due to hydrogen, we'd simply move the decimal over 2 places and get 0.68 again. We're just not going to mess with those times 100 and divided by 100 things. So when we work this out, we end up with 560 millimeters of mercury for the partial pressure of our hydrogen. partial pressure of our oxygen, then we could get it a couple of ways. We could just simply subtract the 560 from 824, or we can take the mole fraction of oxygen times the total, and we end up then with 264 millimeters of mercury for our partial pressure of oxygen. So added together, they should end up being 824, which they are, and that's just a quick way to see that relationship. If we know mole fraction and we know the total pressure, we can find the partial pressures of all those gases. And often we're only studying one of the gases and wanting information about it, so that's an important thing to be able to do. The last quick thing I want to remind us about, and this is from Chem 1, and this is going to apply to the labs that we're doing next week. Often we are collecting a gas to study over water, and we have to remember, let's say we're collecting hydrogen gas in this case. So we're collecting all this hydrogen gas, but the thing we have to remember is that in this container, along with the hydrogen gas, since it's being collected over water, are some water molecules. So we've got to take into account that fact when we're looking at determining the pressure of just the dry gas. Now, we'll work with this. I'm not going to go into this right now. You could look it back up in your Chem 1 information to look up the water vapor pressure table. It changes for each temperature that you're at. The water vapor pressure changes. And simply subtracting off water vapor pressure from your total pressure to get the pressure of just the hydrogen is going to be an important skill we're going to need. But we'll deal with that more numerically later when we get into lab. But right now I want to remind you about how we determine the pressure of this container overall. We've got atmospheric pressure out here. Let's call that P atmospheric. Inside the container, there's a total pressure of the gases. It's going to be hydrogen and oxygen together, but let's call that P inside. Right now, in this top diagram, the pressure outside and the pressure inside are not the same. And the only way we can measure the pressure inside that container is to compare it to the pressure outside the container on a barometer that we have in the room. So how do we make those two equal? The only way to do that is to make sure that the level of the water inside the container and the level of the water outside the container are the same. If those two water levels are the same, then the pressure outside, the atmospheric pressure, and the pressure inside the container are equal. And that'll be an important thing that we'll need to do when we're trying to measure the volume of the gas that we collect in our labs next week. We'll need to make sure that before we cap off that container and measure the volume, that we make the water levels equal first, then cap off that bottom and measure the volume in that container.